welcome, Marco and Bolei. So glad to have you join us. As Sanaz mentioned, Marco is an associate professor at Stanford, where he directs the Autonomous Systems Laboratory. He's also a director of autonomous vehicles research at NVIDIA. And Bolei is an assistant professor at UCLA, focusing on interpretable and safe AI. So you've both worked for many years in autonomous driving and AI research. And of course, the work in that field changes every year. So if you don't mind briefly, tell us, what have you been working on lately?
Well, broadly, I'm working on investigating how we can leverage this new wave of AI across the three main computers of an autonomous vehicle. So basically, the training computer, the simulation computer, the in-car computer, and more specifically, how to leverage foundation models, that has been a recurring theme today as well, to across these three computers, along with all the AI safety implications related to that.
Yeah, I'm trained as a computer vision researcher, but after I started my lab at UCLA, we started doing research in machine autonomy. So right now, my lab focuses more on the intersection of perception and autonomy. So we have done many work on this driving simulation. So we are building an open source driving simulator called MetaDrive. We also care about human factors in this loop. So we have developed a lot of this human in the loop method, like how this agent can learn from human behaviors to improve their behavior.
So in the context of your work and generally the most advanced work for developing autonomous vehicles, development tools are critical, and we also talk a lot about simulation because that is so important in the context of autonomous vehicles. So I would love to understand from each of you, how do you envision the next generation set of development tools for automated driving and with regards to the research priorities that you have?
Well, I think one of the tools that really is poised for innovation is simulation. So, of course, simulation is always touted as the holy grail in robotics. If we had a good simulator that allow us to train and validate our system, that would accelerate robotics and autonomous vehicles tremendously. Yet, simulation is used largely in a relatively limited way, primarily in a replay context, probably not to the extent we would like to. And that was, I would say, the state of the art until maybe a couple of years ago. But then all of a sudden, we have all these exciting tools, from neural rendering to data-driven models for human agents that are really pushing simulation to a point where very realistically we can stimulate the sensors on an autonomous vehicle and start validating complicated interactive dynamics with other agents. So this is a tool that I'm very excited about, that I think can become increasingly more integral in the development of autonomous vehicles.
Yeah, I think simulation will be very important. It's very important over the years, but previously simulation is more like manually designed, right? We manually create those assets, scenarios in some game engines and run those simulation. I think nowadays we have a lot of this neural rendering techniques and also generative AI techniques. So in that case, simulation will become more like data-driven, right? So we can use our mobile phone to scan the environment and load those digital twins in the simulation and run our end-to-end evaluation. So that will be the future of simulation. Another thing to add on that is not only we want to simulate this realistic visual appearance, we also want to simulate this diverse behaviors as well as those safety critical behaviors, which is really hard to collect in real world, right? So if we can create those safety critical scenarios, then we can better evaluate the safety of our driving stack.
So I want to dive deeper into a bit of those, into a few of those. Bolei, your work on Meta drivers, this is the simulation environment that your team has made for training reinforcement learning driving policy. I think it's fairly widely used in the research community. Tell me more about where this work is heading and how is the industry going to benefit from this work?
Yes, so I was trained as a computer vision researcher back at MIT. So when we started doing some research in autonomy, so we noticed it's so hard to publish some research papers in this direction by just using this existing like reinforcement learning platform, such as Atari game or Modular, because this area is heavily dominated by this DeepMind and OpenAI, right? So then we think about how about just build our own platform and benchmarks. So then we start building this new driving simulator such that we can do our research in this machine autonomy. So that's a start of that. So after that, then we improve the features and also open source to the community. Because we noticed right now the most popular open source driving simulator is Kala, but the function is quite limited. So I think then our open source simulator can fill the gap to facilitate the research need of the different researchers. So then nowadays we still developing some new features and also maintain these infrastructures.
Really interesting. And Bolei, you also mentioned the concept of neural rendering. So Marco, I know that your group does a lot of work in this field, and also from NVIDIA. NVIDIA is sort of the ultimate computer graphics company. There's sort of two approaches now for sensor simulation. You can use computer graphics on one side, and that's a fairly well-proven technique. But there's also all of these new neural rendering techniques, which your team has pioneered. Where do you see these two fields going? Do you think that computer graphics will sort of become obsolete in this field, or do you think that these will coexist for some time?
I think they will coexist and they will serve different purposes, but particularly regarding neural rendering, I think those techniques are particularly useful in a world where there is a significant push toward end-to-end architectures. And of course, end-to-end architectures have a lot of potential advantages, but they come with very specific challenges, particularly that of validation. That to validate them, you need to validate them in closed loop, and you don't have intermediate representations that you can use for simulation purposes, so you have to stimulate the full algorithmic pipeline. And that's where you really need to have a highly realistic representation that you can use to feed all your network. And that's, I think, one of the key use cases for neural rendering pipelines broadly.
Really interesting. And you've both also done pretty significant work on the topic of scenarios and traffic generation for simulations and sort of the tooling that surrounds all of that. So what are some of the things that you can do today that weren't possible maybe a year or two ago? What's the state of the art for scenario and traffic generation?
First of all, it's still an open field, right? It's very difficult to generate scenarios, specifically instantiate policies for all the agents that are in the scenario in a way that is grounded in reality. It's as plausible, it's stress-tested system, and is scalable to many different areas of the world. That said, I think there are a number of exciting advancements. One of them is, again, to use foundation models. And for example, we have been doing some work on leveraging large language models to mine all the crash reports that have been written by the police in the United States in the past, and then use a model to read those crash reports and generate scenarios that in some ways replicate those crashes. Of course, with an element of generative AI to populate the scenario with those elements that are not represented in a crash report, like, for example, what is a tree, or what is the exact map layout. I think it's exciting because it provides a way to unleash the power of generative AI in terms of creating scenarios, but also a way to ground these scenarios in reality that has been, in a way, the key challenge in this field. And this is just one example that I can give you.
Really interesting. And I've heard a number of companies using things like the DMV handbook for driving policy input, and it sounds like it's a similar vein.
And actually, we've done similar work in that context to basically allow driving policies to generalize in few shots to other areas of the world with local traffic. Basically, the driving handbook fed as an additional input to accelerate the adaptation process.
And Bolei, I know that you've also done extensive work on scenarios.
Yeah, so for the scenario, I think it should be the atomic unit for this driving data set, right? So for image data set, the images is a unit. And for this driving simulators, I think the scenario should be the unit for that. So in that case, we need diverse scenarios that can cover all kinds of situations, right? So we can use them for evaluation. So many companies, like car companies, release some trajectory data, right? But the issue is a lot of companies, they have their own business, so this data only cover limited regions, right? So there should be some effort that standardize the protocols and the standards of the scenario format. So we have some ongoing work that try to standardize those open source driving data sets. So we published a work called ScenarioNet last year that standardized the trajectory data released by this Waymo New Things, New Plan for different companies. Then we can load them in the simulators and also compare the coverage of the scenarios. Another issue for this scenario that imported from real world is that they lack this interesting behaviors. Because what autonomous driving cares about this tail case, right? So how can we can leverage the simulators to create this safety critical scenario, like some collision or some pedestrian behavior, like jump out of the car, right? Then we can simulate these different scenarios and then use this as a evaluation for our existing driving stack.
Really interesting. And I'd like to talk more about foundation models and large language models. So one of the big advantages of these new techniques is their seeming ability to be able to reason about sort of interesting cases that happen on the road. So Marco, tell me more about how do large language models actually reason about counterintuitive cases? I think you published a paper on this at CVPR, is that right?
Yeah, that's correct. Well, first, I will say more broadly, why are we interested in foundation models for autonomous driving applications? Well, a foundation model is a model by definition that has been trained on raw data, typically internet scale, and in a self-supervised fashion. So basically it provides an opportunity to acquire generalist knowledge that can be then used for the task of driving. So basically, there are two main motivations then to use foundation models. Given the same amount of data, it might perform better because it might show embers of reasoning capabilities, and we do have some papers that corroborate this hypothesis. Or given a required level of performance, it might require less AV-specific data. Actually, we have some studies that show that with only 1% of AV-specific data, we can achieve the same level of performance of state-of-the-art models.
Wow.
And of course, the reason why we can do that is that we can bring to the table all the generalist knowledge that the model has learned, which of course unlocks the possibility of generalizing in few shots to many different environments, many different areas of the world. So these are two complementary reasons about why I think foundation models broadly can be very useful for the task of autonomous driving.
And furthermore on that topic, I mean, how does video generation sort of fit into this? Like video generation versus text generation in the context of these driving models?
That's a great question in the sense that foundation models is just an umbrella term. Yeah. Foundation models encompasses large language models, vision language models, video generation models. And the jury is still out in terms of which model is best for what. The hypothesis behind video generation models is that, of course, if a model can predict very accurately what will happen, it means that it has built a very strong visual representation on the world, on top of which then one can train a powerful policy network. Of course, here we're really scratching the state of the art. So I think it's a great time to be in this field and study and investigate all these different choices that now are available for design.
And we can't talk about, especially in an industry conference, about foundation models without talking about when do we think that these could actually be practical to hit production systems and run on production chips?
Well, let me carefully phrase this answer. So with the new chips that are in the making, it's not unreasonable to think of fielding a foundation model on an embedded device. Of course, we're not talking about huge foundation models, but some maybe foundation model that has been distilling down to a reasonable size that can give you the exact numbers is definitely feasible in the next couple of years or so. I'm sorry if I'm a little bit vague here.
Fair enough, fair enough. And Bolei, I'd love to get your take on the debate around modular versus end-to-end architectures. And where do you think that things will land in the next few years?
Yeah, that's a very interesting question. So modular versus end-to-end driving. I think this really depends on the business model of these different companies. So one example is like Tesla, claim they are doing this end-to-end driving. That is because they have so many Tesla cars running on the road, right? They are collecting this video data from those data collection vehicles. They're also collecting the human driver behaviors that help them correct the behavior of the autopilot system, such that they can run this flying wheel things and keep improving their system. So in a case, this end-to-end driving training with a large number of GPU servers, a good strategy for them. Another example is Waymo, right? So Waymo is running this robo-taxi business. So for their case, they just deployed this robo-taxi in San Francisco, or recently they start running their business in LA. So what they need is just overfit each city, just running their data collection vehicles with this redundant sensor perception system and reconstruct those digital twins, then just run their business within those well-reconstructed situations. So in the case, they probably don't need this end-to-end driving, so because they only deploy on those limited number of cities, right? So in a case, I think different companies need to have their own strategies, approach this autonomous driving, whether modular or end-to-end. Like for our own case, because we are doing this academic research, so we want to simplify things. So we want to, for this traffic vehicles, we just want to simplify this vehicle as a vision in and action out, right? So in the case, we can study some other interesting problems just to use this as a traffic agent. So in our case, we use this reinforcement learning to train this traffic agent. Then we can develop better scenario generation or evaluate the ego vehicle's behaviors. Right? So that is more like a simplification in this case.
And you touched briefly on the topic of scaled compute. So let's talk a bit more about that. Related to scaled compute is the concept of scaling laws, right? Which is oftentimes in machine learning, you can get better performance of the system by improving scale. It could be more data or more compute or a bigger model. So my question for both of you is, how far do you think that this will go? Do you think that scaling laws will apply to self-driving in the same way that they've applied, let's say, to large language models? Or do you think that these are different enough problems that we shouldn't expect the same results? Maybe starting with Marco.
Well, I mean, there are some things that we already know and are being corroborated by a number of studies, like, for example, that high-capacity models can be more sample efficient broadly. In terms of how performance scales, this is actually something that we are actively investigating, particularly in my group at NVIDIA. I don't think there is a consensus yet on this topic, but I do foresee that in the next 6 months or so, there will be a number of studies from NVIDIA and many other players that will constrain your question to, I think, some actionable takeaway.
Mm-hmm. Yeah, so my thought on this is, I think the scaling law in autonomous driving will work differently than the scaling law in this large language model. Like for large language model, you can just collect a lot of this offline data and just train on this offline data. But for this autonomous driving, it's more like this interactive behavior, right? So you want this agent can interact with the real world. So it's more like an interaction. So I think it's hard to train, apply scaling law on this offline videos. We still need more interactions such that the agent or the large model can know how to behave next time. So in that case, I think we will have a combination of this offline data as well as this interaction with the real-world environment as well as the simulated environment. That's why this also the simulation is also very important in this.
And personally, I'm hopeful that the research on the topic of scaling laws will actually bring some clarity. I know myself and many folks in the room, right? We are budget owners of the cloud spend, and oftentimes, especially for training these larger models, the bills can get quite large. And so the better that teams can predict what performance they'll receive before the money is spent, that's better for everyone.
Of course, it's not just the training. It's also, of course, the device that then you use at inference time. So basically how you size it. And I don't agree with the statements made by Bolei, but it's also worth, I think we already have quite a bit of data. Given a certain amount of data, do we want to have a higher capacity model or not? Do we want to have 100 billion models, or do we want to have, 100 million models, or do we want to have 1 billion models? This is still something that people are investigating.
Yeah, and I know there are many leaders in the room today that are actually actively trying to figure out how large of a chip should they put into their next generation vehicle programs. And yeah, very active topic of research. But I'd like to move on to maybe the most important topic in automotive, which is safety. So in general, people are concerned about using the most advanced AI systems, like foundation models, in autonomous driving for production automotive vehicles because they can produce nonsense results, right? You might call this hallucinations. That sounds like a safety risk. But Marco, how can you build a foundation model that's safe? Like, what guardrails do we need to have in place?
Well, first of all, I think there are two different trends that make validation challenging. One is the end-to-end trend, and the other one is the foundation model trend. Of course, these two ideas that sometimes are conflated are different ideas. Of course, you can have an end-to-end model that doesn't use foundation models, or you can have a fully modular stack that uses foundation models for some of its modules. So I think it's important to understand the specific challenges of each. Starting from end-to-end. So the challenge with end-to-end is that if you want to validate it, it's very hard because you need to validate it in a closed loop while actuating your car with the policy that you're validating. In a modular stack, you can rely on open loop KPIs, for example, to validate your perception network. You don't have this luxury with the end-to-end models. So one way to actually decrease the validation challenge is, of course, to introduce some notion of redundancy and diversity in your stack, but in a way that doesn't hamstring the performance of your end-to-end model. So that's one topic. For foundation models, they're not black magic. I mean, they're data-driven models, as I like to say. So as any data-driven model that can get auto-distribution and provide erratic responses, but there are a lot of techniques we have at our disposals to guardrail them in terms of input level monitors, output level monitors, arbitration with other models as well. So there is not a silver bullet, as I like to say, but on the positive side, today we have several different techniques that we can leverage to build, I think, a safety assurance case for end-to-end foundation model empowered AV stacks.
Yeah, so one thing to add to Marco's idea is I think the human factor will be very important in this AI safety, right? So like the humans could be from two sides. One is a human driver, right? So how human driver interact with the autopilot system and how they shift this responsibility. Because basically, if we don't reach this level 5 autonomous driving, so we have this kind of like shared control between human and AI for these vehicles, right? So how can we shift this responsibility between the two will affect a lot about the deployment of this autonomous driving system in real world. Right? Another human factor is this this pedestrians. Right, usually a lot of this accident happen to these pedestrians. So how can we improve the situational awareness and predict the behavior of these pedestrians will be a very important thing for these foundation models.
I agree. I mean, there are ways to articulate a problem. For example, by using ISO terminology, we have different levels of controllability depending on the system that you're trying to design. And of course, depending on whether, for example, you're designing a system that is L2++ hand-free, that translates in completely different requirement for mean time between failure. But that said, yes, all the challenges that Bolei mentioned absolutely apply.
And of course, we want to design these AI systems to be safe from the get-go. But I also wonder, can AI be used to detect things that are not safe, or actually be used to create the safety case itself?
I think that's an excellent point. So Bolei already mentioned the opportunity of foundation models to help on the training side, the data engine side. This is where actually foundation models can also help as a safety evaluator to basically kick off a data flywheel also on the evaluation side. There are a lot of behaviors that are safety critical, but are very difficult to specify just in a procedural way. Like, for example, I don't really want my vehicle to merge the lane in this way, because if the other vehicle were to be inattentive, then I might crash. So these are behaviors that, of course, you want to disincentivize with your model. And unless you have human labelers that are expensive, especially for this type of safety assessment, then you don't have many other tools. That's what actually foundation models that is specifically fine-tuned, starting with some human annotated data, could help big time.
Yeah, I would be happy to have ADAS or foundation models that can help improve the safety of the human drivers. Because we have a lot of crazy drivers in Bay Areas, right? And then how can we use autopilot to improve their behaviors, improve their driving skills will be very important.
Absolutely. And both of you, of course, are stellar academics, but you also have deep ties to industry. So I'd love to talk a bit more about how academia and industry can and should work together better. Maybe Bolei, starting with you, and what are the key differences in how autonomous driving technology is approached in academia versus industry, and how can we actually leverage these differences to actually push forward innovation?
Yeah, that's a very good question. So I think the autonomous driving is one application in computer vision. Right? I'm from computer vision community, but the computer vision researcher will think this autonomous driving pretty much like a solved problem because this is so heavily industry driven. So industry have the data collection vehicles. They are running their vehicles 24/7, right? They're collecting a lot of data, and they build their platform and commercialize this technology. So it's none of business of this academic, like researchers, right? So that's why I have this incentive, like how can we build an open source platform such that the industry can share the data, then academic researchers can use the data to perform this academic research. And we are very good at open source, the prototype we developed and the paper we published, right? So then the industry then further can benefit from those prototypes, improve their robustness of the system, and finally they can benefit their own business. So we want to create this cycles to benefit both industry and academia.
Well, I mean, academia should do what does best, right? So basically develop new methodologies and basically be pathfinders for society. And even though sometimes people say, I mean, what is left for academia? Google has all the compute that you care, and NVIDIA has all the data that you care. No, it's not the case. For example, we've been talking a lot about foundation models. There's plenty of topics related to how we distill down these models, how we improve the inference. On the safety side, many of the techniques are still for example, for monitoring to be developed. So a lot of opportunities in terms of innovation on the methodological side, and academia is well poised to do that. But at the same time, academia also works very well with industry. And this is something that in the United States in particular has been very, very fruitful. Personally, for example, my lab has been working with 2 or 3 automotive companies, and we had very nice papers together. Some of them actually transferred to their stack. So I think that as long as we understand what are the peculiarities and also the roles in society of academia and industry, I think there is definitely a space for both.
So we're almost out of time. I'll ask just one last question. There's a lot of decision makers in the room who are actively making decisions for future vehicle programs. What are the top trends in your fields and research that you think will have the biggest impact on the industry over the next 5 to 10 years?
I think it will be the interaction between the infrastructure and these vehicles. So right now we are doing autonomous driving, and this is more like for the ego vehicles. But these ego vehicles will run on the public road, right? How can the government stakeholders also get involved, and also DOT or Nissan get involved into this? So create these cycles.
And I know that there is a lot of hype regarding Gen AI and foundation models, but I do really think they will have a big impact simply because there are so many use cases. We talked a lot about the software on the vehicle, but in terms of accelerating the training processes with better retrieval services or evaluation or simulation. So sure, some of these use cases won't pan out, but there are so many opportunities that I'm sure that some of them will be home runs. So this is probably a technology that I think is poised to provide big dividends in the future.
Great. With that, Marco, Bolei, thank you so much.